Hello, students. Welcome to this video. I plan to go over some examples doing establishing identities. So let's go ahead and get started. Okay. I wonder if this is going to get in the way, but I hope not. In any case, why don't we go ahead and get started? Okay. All right. So I would like to work some of the examples that we didn't cover in class. And I think it's important for me to do that for the class. And so let's begin with the first example. Okay. So in this case, for number one, the strategy will be um, that we would like to work everything when it seems like there's different trigonometric functions. It's best to try to write them all in terms of sine and cosine. So for example, cosecant of theta will be the same as 1 over the sine of theta times the cosine of theta. And what we're trying to say is that this left side, if we manipulate it enough, is going to look like the right side. And so I want to avoid my algebra techniques. And so let me do a little better here because I feel like this didn't come out as nice. And so if we are manipulating the left side, then times cosine theta, then this results into cosine theta over sine theta, which by our quotient identities, this is the same as cotangent of theta, and therefore the left side must really equal the right side. So therefore that identity has been established. Similarly, with example number 2, we notice that there is a side, which I'm going to try to highlight. There is a side that is a little bit more complex than the other side. And so therefore we're going to manipulate, in this case, the left side, and hopefully make sure that it equals to the right side. So in this case, the strategy will be to take advantage of the distributing property. Okay. And so I will go ahead and distribute. So we get cosine of theta times tangent of theta plus cosine of theta times cotangent of theta. As I said earlier, a good strategy when we have different trigonometric functions, write everything in terms of sine and cosine. And so let's see. So we have cosine theta times sine over cosine plus we have cosine theta times, in this case, we have cosine theta over sine theta. And what we notice here is that we have those two terms will cancel out. We have sine theta plus, in this case, we have cosine square theta over sine theta. And what I notice is that we need to go from two terms to one term. So what I'll do is I'll go ahead and add these two quantities. So it seems like we need a common denominator. Whoops. So we get sine theta. Here we get sine square theta plus cosine square theta. And if you missed it, the reason why this term is now sine squared theta is because we had a 1 here, and so therefore we multiplied it by sine theta, right, times sine theta, and therefore now we can go ahead and add these fractions. So we get 1. So using the Pythagorean identity, that will be equal to 1 over sine theta. And this is the same as cosecant theta. We notice that our ending result is the same as what we had originally. So therefore, this identity has been established. All right, let's go ahead and work now. We did these 2 examples in class, so let's work on example 5. And let's see what kind of jelly jam we can get ourselves into in example 5. So it seems like we need to go. We have one fraction, and it seems like we have a sum, and here we have a product. Okay, so let's see what kind of jelly jam we can get ourselves into. Um, I'll say this: we got to try something, because not doing anything is not going to get us anywhere. And so, okay, we have to manipulate something. I I hope that you agree with me that the left side is more complex than the right side. So let's work over here on the left side and see what happens. And so I'm noticing there's 10. Okay, so let me just write it. So we have tangent of alpha. I don't want to do alpha. I think, I guess we'll do alpha. We'll do alpha. Okay, tangent alpha plus tangent beta over cotangent, oops, not cosine, cotangent of alpha plus cotangent. Why did I think I get so used to writing cosine. So I can see where that's going there. Cotangent beta. Okay, what I'll do first is I'll go ahead and rewrite everything in terms of sine and cosine. So we get sine alpha over cosine alpha. That is this tangent of alpha. And now we have sine beta over sine beta over, in this case, we have cosine of alpha sine alpha plus cosine of beta over the sine of beta. Okay, so it seems like this is getting more jelly jam than, more knotted than our goal, but let's believe in the process. What we find here is it seems like we need to simplify this complex fraction. Basically where a fraction that has fractions within itself. And one way to do that is to use a common denominator, okay? So in this case, if all of these denominators were the same, then we can go ahead and kind of just cancel out the denominators, okay? So let's see what we kind of run into. The common denominator here will be cosine alpha, cosine beta, sine alpha, sine beta, okay? All right, that will be the common denominator. And so let's see what happens. So it seems like, I'm going to have to erase this. I should write it somewhere else, but hopefully that makes sense. So in this case, we're going to multiply by, sine alpha, cosine beta, and sine beta, okay? And so we get, so let me just write that here. We're going to multiply by sine alpha, cosine beta, sine beta. Okay. For this denominator, we will need the cosine alpha, we will need the sine alpha, and we'll need the sine beta. Okay, so same thing here. We need a cosine alpha, sine alpha, sine beta. Here we'll need a cosine alpha, we'll need a cosine beta, and we need a sine beta. And so we need cosine alpha, cosine beta, sine beta. Here we'll need a cosine alpha, cosine beta, sine alpha. So same thing up here. Okay, cosine beta. It will need the sine alpha. And so what happens? So basically, as I said earlier, all of these denominators will just cancel each other out, will just disappear. Okay, just cross out, they go away. Okay, if you do the algebra does work, and there will be no more denominators. So what is left over? What is left over will be the following. Okay, will be the numerators, this numerator over that denominator. Okay, so what does that look like? That looks like this. That will be sine square alpha times cosine beta sine beta plus, what do we get here? We get sine square beta times cosine alpha sine alpha. Okay, what do we get down here? Down here we'll get cosine cosine square alpha cosine beta sine beta plus we'll get cosine square beta cosine alpha sine alpha. All right. Well, let's see. What else can we do here? What else can we do? All right. I would like to get these sine square alphas and things together, but is there anything? What can I do here? Hmm. What can we do? What can we do? Let's think. Let's think. Oops. Okay, so let's see. I have a feeling that we can factor something out here from the numerator, and it seems like we can factor out a sine alpha because sine alpha, and I think we can also factor out a sine beta here, sine beta there. And so let's see, if we factor out a sine alpha, sine beta, we need another sine alpha here. We need a cosine beta plus here we need another sine beta. We need a cosine alpha and no need for the sine alpha. In the denominator, we can factor out a cosine alpha times a cosine beta. Look, both of these terms have cosine alpha, cosine beta. And so here we'll need another cosine alpha times a sine beta plus we'll need a cosine beta sine alpha. Okay. Hopefully this is making sense. And well, this term this term and that term are the same thing. Okay. All right. So maybe you need to pause the video to kind of look at that and to verify that they are the same. They are the same thing. Okay. Even though they may not be written in the same order, but they are the same thing. And so at the end of the story, it seems like we have, let me write up here now. Let me write up here. We have sine alpha times sine beta over cosine alpha cosine beta. And well, this right here will be the same as tangent of alpha. And this right here will be the same as the tangent of beta. And well, yep, we got it. So that is the end of that story. Okay. Alrighty then. I hope that the previous example was recorded. I don't know if I hope it did. Okay. But in any case, I would like to show you one more example. And when we look at this particular, what's going on there? When we look at this example, okay, we notice that the left side seems to be kind of the opposite of what the right side is. Think of it as maybe reciprocal when you're kind of flipping over the fraction. However, I want you to close attention to look at this term and look at this term down here. It wasn't just taking the reciprocal. That particular term switch signs. So what is the strategy here to be able to establish whether the left or right side equals to the other side? And in this particular example, for these type of examples, we want to take advantage of the conjugate. And so for this example, it seems like we wanted to go from left to right. We want to manipulate the left side so that it equals the right side. It seems like we would like to have a 1 plus sign in the denominator. And so what we do is in this example, we want to make the left side look like the right side. So what we do is we multiply by 1 plus sine theta, and then 1 plus sine theta. The textbook, or I think I've seen a couple of textbooks already, where they call this technique multiplying by like a magical number 1. Okay, and why do they refer to it like that? By good choice number 1 or something like that. In any case, why do they say that? Well, they say that because 1 plus sine theta over 1 plus sine theta, this is equal to 1. Okay. All right. So this is, I don't really know if if it has a name. However, the technique is multiplying by a good chosen 1. Okay. And so in this case, the good chosen 1 will be 1 plus sine theta, because it seems like we need a 1 plus sine theta in the denominator. Well, let's believe in the process. Let's see what the process says. In the numerator, we'll get, if we just use FOIL, we'll get 1. So 1 times 1 will be 1. And then we'll get 1 plus sine theta will be sine theta. Negative sine theta times 1 will be minus sine theta. And then we get minus sine squared theta. And down here we have, let's see, I think I want to leave it alone because I don't want to distribute. So I'm going to rewrite it as sine theta 1 plus sine theta. And the reason why I didn't want to distribute is because I'm looking ahead and I'm noticing that I need this 1 plus sine theta. So I'm hoping that the numerator simplifies, and of course here we get a simplification and we get 1 minus sine squared theta cosine theta, 1 plus sine theta. And from the Pythagorean identity, if we move the sine square to the other side, it seems like this is equal to cosine squared theta. Oh. And so therefore we notice that we can simplify that and we'll get cosine theta over 1 plus sine theta. And we notice that it's the same term with the same thing. And so therefore this identity has been established. Okay. All right. I hope that number 5 got made it in the recording some way or somehow. Um, in any case, let me see if I could just try to. I don't think it did. So what I'm going to do is I'm going to try to work fast and see if I can get to a point where I can explain what might have happened. Okay. So here we have. So we're working on the left side. So we have sine alpha. Oh, this is so wrong. Plus, what do we had? We had here sine beta over cosine beta. Down here we had cosine of alpha, sine of alpha, plus cosine of beta over sine beta. And then we had a common denominator, and I think it was up here, it was sine square alpha. And so we needed times cosine beta times, so we did the sine. We need the sine beta here. And then up here we got the we need sine beta, which is what we got, sine squared beta, because you need another one. And then you need sine alpha, cosine alpha. And then over here, we'll need, so since we're multiplying by, okay, so we need a cosine square alpha times cosine beta times a sine beta, I believe. Plus here we needed we'll definitely get a cosine square beta because of that, cosine alpha times sine alpha. Okay, good. I think that's where we got there. And then hopefully that was before. And then right here, I'm going to factor. And so maybe I'll do a little better job here. Notice that this term has a sine alpha, sine beta. This one has sine beta, sine alpha. So I'm going to factor something out. And so this is what it would look like in the numerator. So we factor out I'm going to do sine alpha, sine beta from the numerator. If we factor a sine alpha, we still have a sine alpha there. We don't have a sine beta, but we have a cosine beta. And here's we'll have another sine beta, no sine alpha because it's out here, times cosine alpha. Similarly, in the denominator, let's see, they have something in common. So notice that this is here and that's also there. And so therefore, let's take the pen. We'll do cosine alpha, cosine beta, and we'll need another cosine alpha here, and then a sine beta. Oops, close the parentheses too early. And then we'll need, so a plus. And then here we'll need another cosine beta. No need for the cosine alpha because it's out here, but we'll need the sine alpha. Okay. hopefully these two terms do cancel out, and they do cancel out. Notice that this term is the same as that term. You know, remember the order doesn't matter in multiplication, so this is the same as that. Similarly, this is the same as that. So these two things are the same thing. So they simplify to one. And so then here, that just turns into the tangent of alpha. And this turns into the tangent of beta. And end of that story. I think I did a better job towards the end. In any case, that's it for this. I'll see you guys next week. And thank you.